Welcome to the series Nutrition for Whole Health, lessons on the nutrients that keep our bodies functioning optimally. I'm Thomas Lemke, registered dietitian and the clinical director of Whole Health. This installment is about fats. What is fat? That's a large question, pun definitely intended. We're talking about a class of molecules that gives us energy, provides insulation against the cold, helps conduct nerve impulses, forms our hormones, and literally encases every cell in our body. Doesn't sound terribly important, right? Maybe now I have your attention. And hey, look, a phospholipid. That's a great place to start learning about fats. Let's zoom in for a second. As I said, this is a phospholipid. It has two major components. See that circle up top? That denotes the phospho part, the glycerol backbone that holds onto the fatty acids. We won't be saying much about that in this lecture other than to denote that it's hydrophilic. That means it loves water. Loves it. It's attracted to it. Each glycerol backbone carries two fatty acid tails, those things dangling there below. They can be saturated fats or unsaturated fats, doesn't matter. And we'll talk more about that distinction later. What's important to note right now is that those fatty acids are hydrophobic. No, not rabid, just repelled by water. You know how this works, don't you? You've seen oil, a type of fat, be repelled by water. I'm quite sure of it. In any case, here in this molecule, you've got one side that is attracted to water and one side that's repelled by it. What do you think these guys do in water? One option is for a bunch of these phospholipids to get together and form what is called a phospholipid bilayer. That is, two layers of phospholipids, with the water-loving heads poking out into the water and the water-hating tails safely tucked away in between. And that's exactly what the membrane or skin of every single one of the cells in your body is made from. So you can see why fats are so important. Okay, so now we have some idea about why fats are important. And we know that we get them from our diet. But that opens up the question we're going to spend the rest of our time on. What kinds are there, and why does it matter? As it turns out, there are lots of different kinds of fats. For instance, here are the primary fats found in olive oil. You have oleic acid, palmitoleic acid, alpha-linolenic acid, linoleic acid, palmitic acid, stearic acid, and arachidic acid. Real quick housekeeping. See that section on the left of these with the two red O's denoting oxygen atoms and the H denoting a hydrogen atom? That's called a carboxyl group. Don't worry about remembering that name though. Remember its other name, the alpha end of the fatty acid. Conversely, you see those CH3 sections on the right? The C denotes a carbon atom, where the H3 denotes three hydrogen atoms hanging onto it. This is called the omega end. Remember that, it will be important later. Now, the up and down squiggles denote more carbon atoms, all bonded together into a chain. Each angle is a carbon, and the line to the next angle is a chemical bond. If that's not clear on this graphic, just hold on, I have some slides coming up that will make it more apparent. In any case, here are the main things you'll want to know about the differences between these fatty acids. First, look at the length of each chain. There are three different lengths shown here. Two are 16 carbon atoms long. That's the palmitoleic acid and the palmitic acid. Then we have four that are 18 carbon atoms long. Those are oleic acid, alpha-linolenic acid, linoleic acid, and stearic acid. Finally, we have one that is 20 carbon atoms long. That's arachidic acid. All right, so we've established that one of the things that makes fats different is their different lengths. You may have heard the term short-chain fatty acid, which is often talked about in conjunction with gut health, since they are produced by microbes in your intestines when they are happy and thriving. Short-chain fatty acids feed your enterocytes or gut cells, so they get their name because their carbon chain is so short. Or how about medium-chain triglycerides, or MCTs? These are fats found in coconut oil, for instance, that your body processes into ketones, which are longer than short-chain fatty acids, but not as long as long-chain fatty acids, like the ones you see here on your screen. But Thomas, you may be thinking, Length isn't the only difference between fatty acids, is it? Didn't you just tell us that oleic acid, top left, and stearic acid, middle right, contain the same number of carbons, meaning they have chains of the same length? That's absolutely right. So let's look at the second variable that makes fats different from one another. Notice that extra line on the oleic acid, right there in the middle where the squiggles pause. That extra line denotes that at this site, the fatty acid has a double bond, rather than a normal old single bond. Yeah, chemistry terms, I know. Compare it with the stearic acid on the right. Same chain length, but no double bond. While we're on that stearic acid, look at the number of hydrogens denoted there in that little circle, 36. That is the maximum number of hydrogens a fatty acid of this length can have. It has so many hydrogens, it is absolutely saturated with them. You might even call this a saturated fatty acid. That was a clue. Now, look at oleic acid there on the left again. Check how many hydrogens. 34. Well, that's not the maximum number of 36. That double bond kicked 2 of those hydrogens off of there. This fatty acid is not saturated with hydrogens at all. It's an unsaturated fatty acid. And now you know the difference between a saturated and an unsaturated fatty acid. And look, the more double bonds the fatty acid has, the fewer hydrogens. See linoleic acid there, with 2 double bonds and only 32 hydrogens. Or alpha-linolenic acid with 3 double bonds and only 30 hydrogens. All 18 carbons long, but the variance in number and location of double bonds changes what kind of fatty acid it is. Here's a different representation of fatty acids where the carbons in the chain are more visible. Same as before, each of these has 18 carbons in the chain. But look at the double bonds. Up top in oleic acid we have 1 double bond, and where normally each carbon in the chain has 2 hydrogens hanging off of it, the carbons on either side of that double bond only have 1 apiece, again making this an unsaturated fatty acid. In fact, all of these are unsaturated fats. But notice something peculiar. Off to the right, they are labeled further, with oleic acid being denoted as an omega-9 fatty acid, linoleic being denoted as omega-6, and linolenic acid being denoted as omega-3. Well, now where do these terms come from? Remember what I said about the alpha end there on the left, and the omega end being the last carbon in the tail on the right? Well, if you start counting from the first bond there at the omega end and work your way up the chain, the number you reach where you find that first double bond supplies the omega number. Let's test it. In oleic acid at the top, if we start from the omega end on the right and count bonds, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the first double bond. Oleic acid is an omega-9 fat because that first double bond is in 9th place from the omega end. This holds true for linoleic acid as well, which has its first double bond at the 6th place from the omega end, making it an omega-6 fatty acid. And same for linolenic acid, which has that double bond at the 3rd place from the omega end, making it an omega-3 fatty acid. Now those double bonds aren't just for show. It turns out that their presence or absence imbues some pretty important qualities onto these fats. That story starts by noting that these molecular models, while good and useful, are a little bit deceiving in one key respect. They show each of these fats as running in a straight line. That's done for the ease of fitting everything onto one graphic, nice and neat, but you know what? Those double bonds won't allow it. Take oleic acid, for example. Let me show you what it really looks like. In reality, oleic acid has a bend in it, courtesy of a kink that double bond puts in there. Now, if that bond wasn't there, say in a saturated fatty acid, like stearic acid, then of course it would be straight. So let's think about this. If saturated fats are straight and unsaturated fats are bendy, which kind of chemical properties might this bestow? Think about the fats in the human diet. Some, like butter, ghee, lard, and tallow, are solid at room temperature. Others, like olive oil and vegetable oil, are liquid at room temperature. The reason for this is simple. Straight fats, which is to say saturated fats, are easily able to sit one on another and nestle in nice stable arrangements, meaning that they are solid at room temperature. Unsaturated fats, with the bends in them, are less able to stack neatly, meaning that they do not have the same stability and are therefore liquid at lower temperatures. In fact, the more double bonds in the fat, the lower the temperature required to freeze it or make it solid. This linoleic acid has twice the number of bonds of oleic acid. So whereas oleic acid with its one double bond will solidify in the refrigerator, this one would need to go into the freezer to solidify. And some fats have even more double bonds than this. Look how many double bonds are in these omega-3 fatty acids. See the two on the left labeled EPA and DHA? These are found in fatty fish like salmon, hence fish oil. Salmon need these fats because they swim in frigid waters, where saturated fats in their skin would freeze and become rigid. With all of the double bonds in these fats, however, they stay liquid even in icy temperatures. So, we've learned that the more double bonds, the more unstable, and therefore the harder to freeze the fat is. But there is another consideration that's important to bring up with regard to the instability created by the variable number of double bonds in these fats. The problem is this. Contrary to what you'd expect, the double bonds are weaker than the normal bonds. That means the more double bonds, the weaker the fat, and the more susceptible to oxidation. Oxidation is a chemical process whereby the fat is broken. I'm sure you've heard of broken fats before. We call them colloquially rancid. What breaks fats and makes them rancid? The big offenders are, number one, light. The energy and light going into the fats can cause them to break. Number two, heat. This is another form of energy going into the fat, again, potentially causing it to break. Number three, air. The oxygen in the air can react with the fat, potentially, again, causing it to break. And time, number four. Over time, things break down, and fats are no different. This is why olive oil, for instance, is typically stored in dark bottles with lids to keep out light and air that would contribute to making it go rancid. It's also why you change out frying oil, because all of that heat greatly increases the amount of rancid fat molecules in there. Looking at the slide, you'll see the variety of fatty acids in olive oil, and these will all break down at different rates. The alpha-linolenic acid with its 3 double bonds will break down at an exponentially higher rate than the stearic acid, which has none. Now, of course, olive oil does not have an even distribution of those different types of fats. Most of the fatty acids in olive oil are in the form of oleic acid, that monounsaturated fat which gets its name from olive oil. With only one double bond, oleic acid is overall a fairly stable fat. This makes olive oil a healthy choice for cooking as it does not oxidize and become rancid quickly. Olive oil also has plenty of natural antioxidants that help it protect from oxidation, making it even more stable. Compare that with corn oil, that is majority linoleic acid, a fat with 2 double bonds. Corn oil also contains fewer native antioxidants than olive oil, meaning less protection against oxidation-induced rancidity. Quick story. I was teaching a class over this very subject a decade ago, and one of my students commented that his uncle had worked for one of the major snack chip companies. I won't mention the name, but you know of it. Anyway, he explained to the class how his uncle had worked at this company to run tests on human taste in order to find out how rancid an oil has to become before someone can taste it. Obviously, the reason for this research is because they use such highly oxidizable oils in frying these chips, corn oil, soybean oil, sunflower oil, cottonseed oil, that it's an issue. So they have it down to a scientific process where they let the oil become as rancid as possible before changing it just in time for the consumer not to taste it, to save on the costs of changing it more often. But why do our bodies have an aversion to rancid fats in the first place? Well, it's simple. They are toxic, and our body is disgusted by them, like it's disgusted by many things that are toxic, in order to protect us from consuming them. They create inflammation and contribute to a host of problems, including heart disease, diabetes, Alzheimer's, cancers, and more. You really, really don't want to be ingesting rancid fats. So what's the worst oil for cooking anyway? Well, you already know it if you think about it. It's an edible oil, but one that you'd probably never dream of making fried potatoes in because you'd render them inedible. The answer is fish oil and flax oil. That is, the two oils highest in omega-3 fatty acids. Recall from earlier that omega-3 means that the first double bond is only 3 spots up from the tail, the omega end. That means there are plenty of other spaces for double bonds as well. Let's pull that slide up again. Remember, fish oil on the left and flax oil on the right. Look at those double bonds. DHA has 6 of them. If you tried to cook with fish oil, it would all be over in a hurry. Those fatty acids would oxidize faster than quick. As bad an idea as it is to cook on omega-6 polyunsaturated fat-rich oils like corn oil, or those others we mentioned a minute ago, cooking in fish oil would be an absolute unmitigated disaster, and it would taste terrible to boot. So, we've seen what the worst fats are for cooking, but what about the best? Olive oil was pretty good, but the oleic acid in there still has a double bond that can oxidize. Are there any fats without double bonds that are even more stable? There are, and this is where things get really interesting. It turns out that beef tallow is vastly more stable than vegetable oil of any stripe. Stearic and palmitic acids, which have no double bonds, comprise over 60% of the fatty acids in tallow. Oleic acid, with only that one double bond, as we saw in olive oil, is basically the rest of it, with only a small amount of other assorted fatty acids. Saturated fats, those with no double bonds, have gotten a bad rap, but they're still without question the healthiest cooking oils out there. Butter, lard, beef tallow, and coconut oil all fall within this category, and all will oxidize much more slowly when used as cooking oils. Fun fact, in the early days of McDonald's, in the 1940s when Ray Kroc was taking the franchise coast to coast, do you know what oil they used for their French fries? Beef tallow. However, as the 20th century went on, saturated fats fell out of favor due to fears stoked about its supposed connection to heart disease risk. Because of this, the flight from saturated fats, most of them animal fats, to polyunsaturated vegetable oils was on. Finally, in 1990, the franchise of McDonald's made the switch to partially hydrogenated vegetable oil. What is partially hydrogenated vegetable oil, you may ask? In a word, it's trans fats. Let me explain. Recall for a moment that the double bonds in these unsaturated fatty acids cause the molecule to bend, and make it therefore harder to stack one on the next, making them liquid at room temperature. Here's oleic acid again to demonstrate. Now, that double bond there has a special name, a cis bond, so called because the atoms on either side of the bond bend the same way, creating the curve. But there's another kind of double bond, the trans bond, meaning opposite, where both sides bend in different directions. Here, let me give you a visual. Now, we understand that the oleic acid with the cis bond on top is only straight in this picture for ease of representation. But there you can still see the atoms on either side taking off in the same direction. Compare this to the trans bond on the bottom, where the atoms on either side take off in opposite directions, exactly like a saturated fat would. And indeed, trans fats behave as saturated fats in many respects. They're also straight without that bend, meaning they are solid at room temperature, like saturated fats. And that turns out to be pretty relevant. You see, back in the middle of the 20th century, saturated fats fell out of favor, as I've already mentioned. Ancel Keys showed some, shall we say, cherry-picked data suggesting that saturated fats were to blame for heart disease. Public health recommendations followed suit, encouraging people to avoid saturated fats and replace them with vegetable oils. But there's a problem, because you love Aunt Betty's homemade pie, and Aunt Betty needs an oil that is solid at room temperature to make that pie crust. But vegetable oil is liquid at room temperature. So what can be done? The answer is partially hydrogenated oil. Hydrogenation is the process by which unsaturated fatty acids from vegetable oil are bombarded with hydrogen, so much that in some cases they remove the double bond and stick onto the carbon in its place. However, in other cases, the hydrogen only sticks for a second before bouncing back off and allowing the double bond to reform. But when it reforms, sometimes it flips direction, changing the cis fatty acid above to the trans fatty acid below. The good news is that Aunt Betty can now bake her pie, because since this trans fat is straight like a saturated fat, it is solid at room temperature. The bad news is that an excess of trans fatty acids is even worse for your heart than saturated fats, by a lot. So much so that in 2015, partially hydrogenated oils were taken off of the generally recognized as safe or GRAS list for human consumption by the FDA. You may have noticed a difference in how your margarine behaves since then. Whereas up until this point it was made with partially hydrogenated oils and would sit right on your counter and not melt, now those room temperature stable oils have been taken out. Some modern margarines will melt if left out of the refrigerator, whereas others have added plant gums or pea protein to keep them solid at room temperature in the absence of those trans fats. Oh, and by the way, to McDonald's credit, they stopped using hydrogenated oils in 2007. Unfortunately, their move over to non-hydrogenated vegetable oils is not without issues. On that note, we're almost done with this lecture, but I'll leave you with one last thing that you might want to keep in mind. When it comes to polyunsaturated fats, you want to consume omega-3 and omega-6 sparingly and in balance. What do I mean by that? Well, I say sparingly in large part because these are the fatty acid forms most likely to oxidize, as we saw, whether before you eat it or even in your own body. Pro tip, vitamin E is a fat-soluble antioxidant that can help with this. See my video on vitamin E in the Vitamins for Whole Health series. But when it comes to balance, here's what I mean. Omega-3 fats are processed in your body into anti-inflammatory molecules. This can be good, but it's also possible to have too much of a good thing. Omega-6 fats are processed into pro-inflammatory molecules. This can be a bad thing, but believe it or not, it can be a good thing required for healing and fighting infections as well. There's a bit of a yin and yang relationship here. In fact, to stick with that theme, we'll call omega-3s the sun fats. When it comes to plants, the bottom of the food chain, these are generally highest in the parts of the plant that are photosynthesizing in the sun and contributing to the plant getting bigger, namely leafy greens. And we'll call omega-6 fats the moon fats. These are highest in the parts of the plant that are dormant, sleeping, waiting to be woken up, that is, seeds and grains. The very same seeds and grains like corn, soy, safflower, cottonseed, and sunflower, from which we get the vegetable oils McDonald's uses in their fries, in point of fact. Now, it's important to your body that these two types of fat, the sun and the moon fats as we've called them, be balanced for optimal health. Ideally, you want about 2 parts omega-6 to 1 part omega-3 for best results. Higher amounts of omega-6 lead to the type of inflammation implicated in heart disease and diabetes. Hence, calling vegetable oils heart healthy is actually 180 degrees opposite of the truth. But you know what? Because of the way we raise our food animals, stuffing them full of corn and other grains, whether they are lactating, laying eggs, or about to be slaughtered, our animal foods are overladen with omega-6 moon fats, to say nothing of our French fries. This chart shows the results of multiple studies which compared that omega-6 to omega-3 ratio in cattle according to their dietary regimen. Ideally, you want your omega-6 and omega-3 intake to be, again, 2 to 1. 2 parts omega-6 to 1 part omega-3 for best health. As you can tell from the chart, the beef from animals fed on a natural grazing diet consistently achieved that 2 to 1 ratio, give or take. Meanwhile, the grain-fed beef consistently had very, very high omega-6 content compared to its omega-3 content. This holds true for other animals and other animal products as well. So what's the takeaway? Simply that when it comes to this fatty acid ratio, grass-fed pastured animal products are superior for our health. That said, there is a get what you pay for component, as these products do tend to be more costly than their grain-fed counterparts. So they may not be realistic for everyone, at least not all of the time. That's about it. Again, omega-6 fats, try to avoid. We typically get too many of them in our modern American diets. Omega-3s, you can get that from eating a couple servings of fish a week and help balance yourself out with all the other recommendations I've already provided. Now, you know more about fats than you ever wanted to, but hopefully it will help you make more informed choices for your life and health. Thank you for watching the fats installment of the series, Nutrition for Whole Health. We'll see you around.